To each polynomial, we can associate a Galois group. We construct a field extension by adjoining the roots of this polynomial. Since this field extension is normal, we will consider its Galois group. This Galois group will act by permutations on the set of roots of our polynomial. Let us begin by recalling some irreducibility criteria for polynomials. Let f be a polynomial with rational coefficients. We can always find a rational scalar c, which is non-zero, such that c times f becomes a polynomial with integer coefficients, and the greatest common divisor of coefficients of cf is equal to 1. Of course, when we do this, irreducibility in Q of x does not change. So without loss of generality, we assume that f is already such a polynomial. So f of x is an x to the power n plus a1x plus a0 with ai's in z, and greatest common divisor of all the coefficients is equal to 1. Then the first property is that f is irreducible in Q of x if and only if such a polynomial f is irreducible in z of x. We have an irreducibility criterion which is based on reduction mod p. So let p be a prime number. And suppose that the leading coefficient an is not equal to 0 mod p. Consider a reduction mod p of each of the integer coefficients. Let f bar be a polynomial in zp of x, which is obtained from f by reduction mod p. So f bar is equal to f mod p. If f bar is irreducible in zp of x, then f is irreducible in z of x, and thus in Q of x as well. So example, we have the polynomial x cubed plus x plus 1 is irreducible in z2 of x. This implies that the polynomial 7x cubed plus 4x squared minus x plus 3 is irreducible in z of x. This result is obvious because any factorization in z of x by reduction mod p will produce a factorization in zp of x. The next result that we recall is not as obvious and is called Eisenstein's criterion. Again, let p be a prime. Suppose that the leading coefficient an is not divisible by p. All other coefficients an minus 1 through a0 are divisible by p. But the constant term a0 is not divisible by p squared. Then f is irreducible in z of x. As example, let's consider x to the power of 5 plus 4x plus 2. Here, the leading coefficient is 1, so it's not divisible by 2. All other coefficients are even, and the constant term is not divisible by 4. So by Eisenstein's criterion, this polynomial is irreducible. Another property that may come handy is shift invariance. So if we take a an integer, then f of x is irreducible if and only if f of x plus a is irreducible. It may happen that Eisenstein's criterion is not applicable to a polynomial f of x, but is applicable to one of its shifts. Let us consider an example. So let p be a prime and consider a polynomial f of x, which is x to the p minus 1 plus x to the p minus 2 plus x plus 1. Clearly, we cannot apply Eisenstein's criterion to this polynomial for any prime. But note that this polynomial can be written as x to the power of p minus 1 divided by x minus 1. This follows from a well-known formula for the factorization of x to the p minus 1. Now let us look at the polynomial f of x plus 1. So this will be x plus 1 to the power of p minus 1 over x plus 1 minus 1. Now this equals 1 over x times the sum k goes from 0 to p choose k times x to the power of k minus 1. And this becomes, the leading term is x to the p divided by x, so we get x to the p minus 1, plus a binomial coefficient p choose 1 times x to the p minus 2, plus binomial coefficient p choose 2 times x to the p minus 3, plus we'll have a term p choose p minus 1, and the last term with p choose 0 will cancel. We have 1 minus 1. Now what we see here is that the leading coefficient is not divisible by p. Then all other coefficients are now divisible by p. And the constant term a0, which is p choose p minus 1, is equal to p. So this is not divisible by p squared. And now by Eisenstein's criterion, this polynomial is irreducible. And by shift invariance, the original polynomial that we considered is also an irreducible polynomial. Next, let us look at Galois groups of irreducible polynomials of low degrees. Suppose degree of f is equal to 2. And as an example, let's take x squared plus 2x plus 5. Let us find the roots of this polynomial. We can write this polynomial as x plus 1 squared plus 4, and we equate this to 0. Then x plus 1 squared is equal to negative 4. If we extract square root, we get x plus 1 is equal to plus minus 2i. And then we get the roots alpha 1 and alpha 2 are minus 1 plus minus 2i. So the splitting field of this polynomial is E, which is Q with adjoint minus 1 plus 2i and minus 1 minus 2i. But this is just the same as Q adjoined with I. the Galois group will permute these two roots, and this group has two elements. It has identity, and it has a permutation sigma, where sigma of -1 plus 2i is equal to -1 minus 2i, and sigma applied to -1 minus 2i is equal to -1 plus 2i. So it's clear that sigma of I is equal to -i, and we can interpret sigma as a complex conjugation. Let us look at a slightly different example. So let's take x squared plus 2x minus 5. If we want to find the roots of this polynomial, we write it as x plus 1 squared minus 6. And then x plus 1 squared is equal to 6. So x plus 1 is equal to plus minus square root of 6. And the roots alpha 1, 2 are -1 plus minus square root of 6. So the splitting field of this polynomial is q with a joined square root of 6. And the Galois group again permutes these two roots. So it will be a group with two elements, so identity transformation and tau. So it's isomorphic to the group S2 of permutations on a two-element set, and tau applied to square root of 6 is equal to minus square root of 6. And of course, tau restricted to rational numbers is identity transformation. So we see here that if f is an irreducible polynomial of degree 2 in Q of x, then its Galois group has order 2, and it's the group S2 of permutations of the roots of this polynomial. Let us now consider a general situation. So suppose f of x is irreducible in z of x, and degree of f is equal to n. We can factor this polynomial over complex numbers. So we have f of x is equal to an, the leading coefficient, times x minus alpha 1 times x minus alpha 2 times x minus alpha n, where alpha i's are complex numbers. And we know that since f is irreducible, then this polynomial has no multiple roots. So alpha I is not equal to alpha j for I different from j. Our splitting field E is the field of rational numbers with the joined roots alpha 1, alpha 2, alpha n. If we take two roots and consider extensions q with alpha 1 and q with some other alpha I, then these two field extensions are isomorphic because they're both isomorphic to q of x, quotient by ideal generated by polynomial f. Then we can consider an isomorphism map, sigma from q of alpha 1 to q of alpha I, such that sigma of alpha 1 is equal to alpha I. By homomorphism extension theorem, this sigma extends to an embedding of E to algebraic closure of Q. And by the way, perhaps here instead we should have said not complex numbers, but algebraic closure of rational numbers, which is a subfield inside complex numbers. This extension of sigma will still map alpha 1 to alpha I. And since E is normal over Q, being the splitting field, we have that sigma of E is in fact equal to E. And we have the following conclusion, that there exists an element sigma in the Galois group of E over Q, such that sigma of alpha 1 is equal to alpha I. So this means that with elements of a Galois group, we can map alpha 1 to any other root of this irreducible polynomial. This means that all these roots form a single orbit under the action of the Galois group. And we obtain the following important theorem, that Galois group of irreducible polynomial f in Q of x acts transitively on the set of roots of f. And we get a corollary. So if f is irreducible of degree n, then the order of the Galois group of f is divisible by n. This follows from our orbit stabilizer formula, that the order of G is equal to the length of the orbit of an element alpha 1 times the order of the stabilizer of element alpha 1. And since we said that the Galois group acts transitively on the set of roots, the length of the orbit is equal to n. And for this reason, the order of the Galois group is divisible by n. So summarizing is that f is irreducible of degree n in Q of x, then Galois group of f is a transitive subgroup of the group of permutation on n letters. Clearly, the action of any element of the Galois group is determined by what it does to the roots of the polynomial f. So any element of the Galois group may be viewed as a permutation. Let us consider the case when the degree of our polynomial is equal to 3. And of course, f is irreducible. What can we say about the Galois group? So the Galois group is a subgroup inside S3, and the order of this group is divisible by 3. Then we have two options. So one, it is possible that G is equal to S3. And two is that G is a cyclic subgroup generated by a 3 cycle, 1, 2, 3. Clearly, such a cycle will act transitively on the set of roots. This group may be viewed either as Z3 or as the alternating group A3, because the 3 cycle is an even permutation. We would like to understand when, for an irreducible polynomial of degree 3, the Galois group is isomorphic to A3, or more generally, answer the following question. For which irreducible polynomials of degree n, the Galois group is a subgroup in the alternating group AN of even permutations. We give the following definition. A polynomial T in n variables is called symmetric if for every permutation sigma in Sn we have that T of x sigma 1, x sigma 2, x sigma n is equal to T of x1, x2, xn. So that is, if we permute the variables of this polynomial, then the polynomial does not change. Let us give some examples of symmetric polynomials. The polynomials in this example are called elementary symmetric polynomials. So the first one is T1 of x1, xn, which is just the sum, x1 plus x2 plus xn. It is clear that if we permute the variables, then the sum wouldn't change. The polynomial T2 of x1, xn is the sum in I less than j, and these are between 1 and n, of xi times xj. The polynomial T3 of x1 through xn is the sum over I is less than j and less than k of products xi times xj times xk. And finally, the elementary polynomial Tn of x1, xn is the product x1 times x2 times xn. We have the following proposition. Let alpha 1, alpha n be roots of irreducible polynomial f of degree n. And let T be a symmetric polynomial. Then T evaluated on alpha 1, alpha 2, alpha n has value in rational numbers. Let's give a proof of this fact. We know that the set of elements of E that are fixed by all elements of the Galois group is our base field Q. If we take sigma an element of the Galois group of the polynomial f, then sigma applied to T of alpha 1 through alpha n is going to be T of sigma of alpha 1, sigma of alpha n. But the element of the Galois group permutes the roots, and we can think of it as a permutation on the indices. So this can be written as T of alpha sigma of 1, alpha sigma of n. But our polynomial is symmetric, so this is equal to T of alpha 1, alpha n. So this means that the value T of alpha 1, alpha n belongs to the fixed point set, so that is, it belongs to the field of rational numbers. What can we say about the values of elementary symmetric polynomials on the roots of a polynomial f? The answer is given by the following Vieta's theorem. Let f be equal to x to the power n plus an minus 1 x to the n minus 1 plus a1x plus a0, and is also equal to x minus alpha 1 times x minus alpha 2 times x minus alpha n. Then tk of alpha 1 alpha n is equal to minus 1 to the power k a n minus k for k from 1 to n. Indeed, let us look what is the coefficient at x to the n minus 1. On one hand, it's equal to a n minus 1. On the other hand, so here when we expand this product, we should pick the factor of x in n minus 1 terms and the factor minus alpha I from one of these terms. And then we get that the value of coefficient a n minus 1 is equal to minus alpha 1 minus alpha 2 minus alpha n. So this means that t1 of alpha 1 alpha n is equal to minus a n minus 1. Likewise, when we compute the coefficient at x to the n minus 2, we need to pick two factors out of these n factors and take minus alpha I and minus alpha j from these two factors. And then we get that the coefficient a n minus 2 is equal to the value of symmetric polynomial t2 on the roots of the polynomial f. Perhaps to see this better, we could write that a n minus k is equal to tk of minus alpha 1 minus alpha 2 minus alpha n. The constant term of this polynomial a0 is equal to minus 1 to the power n times the product of the roots of this polynomial. And the product of the roots is given by the elementary symmetric function Tn. Since our polynomial has coefficients in Q, this Vieta's theorem agrees with our proposition. We get that the values of elementary symmetric polynomials are rational numbers. The set of symmetric polynomials forms a ring because the sum and the product of symmetric polynomials is symmetric. Let us quote the following fundamental theorem about symmetric polynomials. The ring of symmetric polynomials in n variables is the polynomial ring Q of t1, t2, tn. So that is every symmetric polynomial may be expressed through elementary symmetric polynomials. And elementary symmetric polynomials are algebraically independent, so this means that there are no relations between them. This gives us an alternative proof of the fact that the value of a symmetric polynomial on the roots is a rational number, because this is true for elementary symmetric polynomials by Vieta's theorem, and then any symmetric polynomial may be expressed in terms of elementary symmetric polynomials. Let us consider the following polynomial in n variables. Theta of x1 xn is equal to the product over I less than j of xi minus xj. Let us ask a question. Is this a symmetric polynomial? Well, let's consider the case. N is equal to 2. Then theta is equal to x1 minus x2. Well, is this symmetric? Well, clearly not, because if we permute the indices 1 and 2, we're going to get minus theta. So this is not symmetric. And we easily can get the following lemma, that theta of x sigma 1 x sigma n is equal to the parity of sigma times theta of x1 xn. To prove this lemma, we look at adjacent transpositions. If we transpose indices I and I plus 1, then clearly in this product there will be exactly one term that will switch sign. It will be the term xi minus xi plus 1. And then we see that this lemma holds for these adjacent transpositions. But it's a well-known fact that the whole symmetric group is generated by adjacent transpositions. So thus, this claim holds for any permutation sigma. As a corollary, we get that if alpha 1, alpha n are the roots of a polynomial of degree n, f in Q of x, then theta squared of alpha 1 through alpha n is a rational number. Indeed, we see that the polynomial theta may switch sign when we apply the permutation sigma. However, if we consider theta squared, then we will get equality here. And so this means that theta squared is a symmetric polynomial. And then, by an early result, we get the claim of this corollary. And we give the definition that theta squared of alpha 1, alpha n is called the discriminant of the polynomial f. Let's look at an example when n is equal to 2. So suppose f of x is equal to ax squared plus bx plus c. If we want to factor it, then we have that x minus alpha 1 times x minus alpha 2 is equal to x squared plus b over a x plus c over a, because these two polynomials have the same roots. And then by Vieta's theorem, we have that alpha 1 plus alpha 2 is equal to minus b over a, and alpha 1 times alpha 2 is equal to c over a. So what is the discriminant in this case? So theta squared of alpha 1, alpha 2 is equal to alpha 1 minus alpha 2 squared. This is equal to alpha 1 squared minus 2 alpha 1, alpha 2 plus alpha 2 squared. Or that's alpha 1 squared plus 2 alpha 1, alpha 2 plus alpha 2 squared minus 4 alpha 1, alpha 2. So this is alpha 1 plus alpha 2 squared minus 4 alpha 1, alpha 2. And then applying Vieta's theorem, we get b squared over a squared minus 4c over a. Or bringing this to a common denominator, this gives us b squared minus 4ac over a squared. Not surprisingly, here we see the expression that appears under the square root of the formula for the roots of a quadratic equation. Let us now state a theorem that answers the question that we posed earlier. So we have a theorem. The Galois group of a polynomial f of degree n is a subgroup in the alternating group an if and only if theta squared of alpha 1, alpha n, which is a rational number, has a square root in the field of rational numbers. So if the discriminant of a polynomial is itself a square of a rational number, then the Galois group consists of even permutations. And if the discriminant is not the square of rational numbers, then the Galois group will contain odd permutations as well. Let's give a proof of it. So suppose the Galois group of F is a subgroup in the alternating group. Then for every sigma in the Galois group of F, we have sigma applied to theta of alpha 1 alpha n is equal to theta of alpha 1 alpha n, because in general we have a change of sign given by the parity of sigma, and if all sigmas in the Galois group are even, then there is no change in sign. And then this tells us that theta of alpha 1 through alpha n belongs to the subfield in E, which is fixed by the Galois group. And by Galois correspondence theorem, this is the field of rational numbers. So this shows that the discriminant theta squared has a square root in the field of rational numbers. Conversely, if the Galois group of F has an odd permutation, then sigma of theta of alpha 1 alpha n is equal to minus theta of alpha 1 alpha n, which tells us that theta of alpha 1 alpha n does not belong to Q, the fixed point set under the action of the Galois group. And then we see that the square root of the discriminant does not belong to the field of rational numbers. If we have a cubic polynomial, x cubed plus a2x squared plus a1x plus a0, then by change of variable, so if we set the new variable x tilde to be x minus 3a2, then it's easy to check that we get a polynomial with a zero coefficient at x squared. Clearly, when we make such a change of variables, the Galois group of the polynomial does not change. And for some computations, it's easier to work with polynomials with a zero coefficient at x squared. So let's assume that. So suppose we have polynomial f, which is x cubed plus ax plus b. Then I give an exercise for you. Show that the discriminant of f, which is theta squared, which is alpha 1 minus alpha 2 squared times alpha 1 minus alpha 3 squared times alpha 2 minus alpha 3 squared is equal to minus 4a cubed minus 27b squared. In order to establish this result, one would need to expand this expression and express it in terms of elementary symmetric polynomials, and then apply Vieta's theorem. By Vieta's theorem, here alpha 1 times alpha 2 times alpha 3 is equal to the negative of the constant term, minus b. Then alpha 1 times alpha 2 plus alpha 1 times alpha 3 plus alpha 2 times alpha 3 is equal to a, and alpha 1 plus alpha 2 plus alpha 3 is equal to 0, because we don't have the term with x squared. So we get the following result. an irreducible polynomial x cubed plus ax plus b has Galois group A3, which is isomorphic to Z3, if and only if the discriminant theta squared, which is minus 4a cubed minus 27b squared, is a square of a rational number. Let us now look at an example with a polynomial of degree 4. So let's consider x to the power of 4 minus 2. This polynomial is irreducible by Eisenstein criterion with p equals 2. This polynomial has the following factorization. X to the power of 4 minus 2 is equal to x squared minus square root of 2 times x squared plus square root of 2. Or this can be factored further as x minus fourth root of 2 times x plus fourth root of 2 times x minus I times fourth root of 2 times x plus I fourth root of 2. Then the splitting field of this polynomial is rational numbers with a joined fourth root of 2 and I. Let us consider a chain of extensions. So we have q extended by q with fourth root of 2 and then extended to e, which is q with fourth root of 2 and I. The degree of the first extension is equal to 4 because the minimal polynomial of the fourth root of 2 is x to the power of 4 minus 2, which is irreducible. So here we have an extension of degree 4. And here we have an extension of degree 2 because the minimal polynomial of I is equal to x squared plus 1. And clearly this extension is proper because the intermediate field is real while the splitting field is not. So here we have degree 2. And by multiplicativity of degree, we conclude the degree of E over Q is equal to 8, which tells us that the Galois group of E over F or over Q has order 8 because the order of the Galois group is equal to the degree of the Galois extension. And this Galois group is a transitive subgroup in S4. And the order of S4 is 4 factorial, which is 24. This tells us that this Galois group is a Sylow 2 subgroup in S4. So recall that all Sylow P subgroups are conjugate and hence isomorphic. And we know that D4 is a subgroup in S4 of order 8. So this tells us that the Galois group of this splitting field is isomorphic to the dihedral group D4. Now, what is the geometry of this situation? So if we plot this on a complex plane, so here we have 4 roots. 4th root of 2, then 4th root of 2 times I, minus 4th root of 2, and minus I times 4th root of 2. These 4 roots will form a square. And the dihedral group is the group of symmetries of this square. How can we describe the elements of this Galois group? So suppose sigma belongs to the Galois group of E over Q. Then this automorphism sigma is determined by its action on the generators, 4th root of 2 and I. And we note that sigma transforms 4th root of 2 into one of the following 4 elements. 4th root of 2, 4th root of 2 times I, minus 4th root of 2, and minus 4th root of 2 times I. Whereas sigma of I will be either I or minus I. So we see that we have 4 possible values for the image of 4th root of 2 and 2 possible values for the image of I. So the maximal possible number of combinations of values here is 8. But we know already that the order of this Galois group is 8. So this means that any pair of these combinations can be realized. Let us consider the following element. So suppose tau sends 4th root of 2 into 4th root of 2 times I, and tau sends I to I. Then what is tau of 4th root of 2 times I? So this is tau of 4th root of 2 times tau of I, and then this is equal to minus 4th root of 2. Then what is tau of minus 4th root of 2? Well, by linearity, this is minus 4th root of 2 times I. And finally, tau acting on the last root, minus 4th root of 2 times I, will give us 4th root of 2. What is the geometry of this transformation? So we see that tau is a rotation of the square by 90 degrees counterclockwise. So this element generates a subgroup H of order 4. And this subgroup is isomorphic to Z4. Now let us look at the fixed point set under H. Let us denote this field by K. So we know that the degree of E over K is equal to the order of the group H, that is 4. Then this tells us that the degree of K over Q is equal to 2. And since tau of I is equal to I, we see that I is an element of K. And because the degree of this extension is 2 and the degree of element I is equal to 2, from here we conclude that K is Q adjoined with element I. We point out that a subgroup Z4 is normal in D4. This is because any subgroup of index 2 is normal in any group. And this is reflected in the fact that the field K, Q of I, is a normal extension of the field of rational numbers. And to conclude, I give you an exercise. List all subgroups in D4 and determine the corresponding subfields in the field E.